record on this computer. Let me go ahead and put up attendance for everybody. Start check-in. All right. So this should be the last chapter of the book that features a lot of stuff from the textbook. So let me go ahead and just talk about my plans for the upcoming kind of for the rest of the semester, since I think we're like at the halfway point or something, right? All right, so attendance is running, right? We're like at the halfway point, I think. So let's go ahead and take a look. We've got modules, and if we look over here under module 8, we're talking about dictionaries, which corresponds to, I think, chapter 11 in your textbook. I went ahead and already posted the videos for it. I posted those on like Saturday evening. I'll have a quiz up later this week, probably by tomorrow evening, and it will be on dictionaries and if I can figure out how to do file reading, then it'll be on file reading as well, probably something like a word count problem. Otherwise, I'll just simply give you a large string of text to do a word count on. Word count is a very common problem. Your lab this week, which we'll be giving out on Friday, is Hawaiian pronunciation. After that, I'll be going over a module that I really like, which is kind of my own thing, which is Monte Carlo approximations, which means math doesn't need to be hard in order for you to, just because the math looks hard doesn't mean you actually have to do hard math. And that corresponds to a portion in Runestone. Specifically, it corresponds to chapter 12, to this project 12. So it corresponds to a project in the textbook, but not necessarily a full chapter. After that, so let's see. So that's this week, then next week, and then this upcoming week, I'll start like my goal, and then I'll see what else we need for this last week. And my goal for all of November is that basically that's when we'll start talking about the final project at the end of October. And then the idea here is that during those upcoming weeks, I'll be giving you resources on how on various things you want to do for your final project. If you want to do a video game, then I will show you the resources for building stuff with Pygame on how to build various video games. If you want to try doing something with music, I'll talk about that. If you want to do a website of some kind, and I'm busy trying to figure out what my expectations for this. You don't have to have an idea yet of what you want to do for your final project. So, but the idea is that I'm going to give you basically all of November to do it. With some various tools is the idea. Where'd my chat window go? It always disappears on me. So, as specified in the syllabus, the final project is either solo or group. You get to choose. So you get to make your decision as to whether or not you have a solo project or a group project. But so if you want to do something web-based, I plan on grabbing some tutorials from the CS50X course at Harvard. I can't help you at the moment, Laser. Sorry. But like here, this is an entire thing on how to build an HTML page with there's all these different videos on how to do an HTML page, how to use Flask, which is a Python framework for building a web server. So basically, you can run everything you need with Python. If you need to learn SQL, then there's a module on that, but you probably won't need SQL. But the point being is that there's lots of options for you to do. It's okay if you're overambitious and can't fully deliver. That's fine. We will have various checkpoints through November to help with that. If you want to try doing some basic data analysis, you can do that. If you want to do something more creative, right? There's Magenta TensorFlow, which is what I've discovered over the weekend, which is all about using machine learning. Here, it's in Python, and you've got, try it live, right? Which opens up with something called a Jupyter Notebook, which this is Python. This is, and essentially you just run it. Here it goes and adds notes, and right, this is just essentially a notebook full of Python code that you can run. So with a lot of useful libraries. So if you want to do something musically interesting, please feel free, because I love that stuff. In a similar vein, like, I mean, I'm learning, like, so I found this over the weekend as well, like the DAW that I use, which is like an IDE for Works, which is like an IDE. There's no link for this on Canvas yet for the final project. I'm just kind of talking about what's going to come in November. Okay. If it's a group, yes. If I expect it to be commensurately bigger, equal to the number of people there are, with a maximum of 3 people. So I'd expect 3 times as much, something 3 times as impressive. So, but anyway, I was playing around with my DAW, and I noticed that this had script output over here. And it looks, and it might be hard to see for you, but it says interpreter over here, enter a command and output. And it's a little Python, and it's a Python interpreter built in to my application here for communicating with hardware. I'm still figuring out how to play with it more, but that's something that is something I'd like to look at. So there are a lot of different things here. Build your own Google. You can try doing that and loading up your own web page and doing that. There are a lot of very powerful things you can do. And so I'm going to be very excited to see what you come up with, but more details. Don't worry about it being like, oh God, I don't know what to do. Here's an example of something I would find kind of amazing. This was at a hackathon. So somebody spent basically 3 days doing nothing but programming, essentially, and they had no knowledge of web frameworks going in. And by the end of it, they had created a website that essentially that basically had a GIF from Nickelodeon playing in the background, and every 3 seconds it would change. Okay. So it would just change a GIF of various cartoon characters from Nickelodeon cartoons from the 90s, just changing every 3 seconds or so. And if they were eating something you wanted to eat, you press the button on the only button on the web page. And what it would do is that it would get your location from your IP address, and then basically enter into Google and show you all the restaurants where you could find that particular food. So in other words, it was just it was a button that hooked into a Google Map search, and depending on what GIF was playing at the time, it was able to show you something. And that was, again, this person had no web programming experience. They basically had your amount of experience. Python makes things easy to do like that. This module, which we're going to talk about, dictionaries, is all about making these things easy to do. So we will work on Roman numerals on Thursday, which will go over a lot more about how dictionaries work. Today, what we're going to work on is exploring common words in SETI, which I haven't fully read. And there's a link in there about graphing with Altair, but we'll ignore those portions because unless you want me to show you how to graph stuff, but because I know how to use matplotlib for that. So let's go ahead and pull up today's exercise, which is exploring common words and SETI. So there are a lot of words in the English language. There's so many that we have this book called a dictionary that holds all those words. And so in this project, we will answer a few interesting questions about the English language making use of a list of 5,000 most common words. So what this is that it's from the Word Frequency Data Project, which basically went and analyzed certain basically word frequencies and how often words occur in the English language in web pages, magazines, fiction, academic writing. And one big thing that we see here is that there's this, and so what does this have to do with the search for extraterrestrial life or extraterrestrial intelligence? It says that basically that there's a relationship called Zipf's law that we see in communications, which is that words aren't evenly distributed across a language. For instance, I don't use the word extraordinary as often as I use the word for, because I use a lot of because I don't have a lot of extraordinary sentences. But as a teacher, I use a lot of for instance, or for example, or to be even more concrete, how many times? I mean, think about those special words, articles, a, and, the. Those occur a whole lot. I need to walk the dog. Right? Those the occurs a whole lot. So there's a nice straight line plotted on a log scale that links common and rare words. The slope of, so it's the logarithmic scale. So, and it says that if we look at this in it's not just true human communication, but like if we look at bottlenose dolphins and whales, you get these kinds of communications with the signals we get from them. Okay, so in this lab, we'll look at what are the most 10 commonly used words. How does the frequency usage of the most common words compare to the least? So in other words, how common are some words versus other words? What percentage of the language, of English language, do those top 25 represent? And then create a plot about that. But we can ignore the plot. We might go into that depending if we have time. So we've got this data file already loaded into so what's nice about this is that we've got this data file, a CSV file, like a file we've been working with for the past couple weeks, right? And this is just a CSV file of 5,000 words, right? And what's nice is that since we're working in the textbook, we don't have to download anything. We can just simply say, okay, file is, or I can say open. And then I can say, what's the name? I don't know. I don't want to bother remembering it. So I'm going to copy the name, quotation, paste, quotation, put in read mode. Okay, and data is equal to. And then let's save and run it. And if it crashes horribly, then something went wrong, right? It'll crash horribly if I did this, right? File not found exception. But since it didn't yell at me, I can assume it worked, right? Excellent assumption. In fact, let's go ahead and print data, which should get me a text IO wrapper, right? So let's go ahead and take a look at this data. So our data of words in our list are in order. So they're already in order for us from the most frequency used to the least, where the rank order is a function of both frequency and what's called dispersion, which means how evenly the word is spread across. So in other words, right, you can see like in an academic text or in a biology text, you might have cellular used a whole lot in a biology text, but you're not going to use cellular a lot in architecture, in some architecture or a children's book. Well, maybe if it's a weird children's book, but anyway. So but the point being is that basically, so but words like they'll appear in a bunch of text in a bunch of the text, but words like academic will appear pretty primarily in stuff concerning itself with academic works. So and so 1 means it's very evenly distributed. You find it in pretty much everything. 0 means it doesn't really appear all that often. So if we look at the appears with a 0.98 dispersion. So it's pretty much everywhere. Whereas we look at, say, something that's less common, pistol appears in has a dispersion of 0.98. So it looks like the dispersion doesn't really vary too much in terms of 1 to 0, but it does vary a lot in the 0 to in the 90 to the 0.9 to 0.1 range. Okay. So then they also have, so they have rank, word, part of speech, how many times it occurred, the frequency, and the dispersion. So in other words, we've counted in all their documents, they counted the to occur 22 million times, and then, well, 38,000 change. Okay. So these are just article. So article, verb, conjunction, preposition, infinitive, pronoun, X, not, or doesn't. All right. So there's different kind of things built into there. So, so the example, the word RE has a frequency of 15,000, but only 0.47 because it's primarily used in legal writing. So the first task is to read this file and store the contents into 5 lists. Remember, as you reach each line of the file, the line will be represented in a string. Your goal is to split this line into 5 parts and put each of those parts into the respective list. Okay? So let's go ahead and start there. You can find this document, for those of you who can't find it. It is on your runes. So one way to get to it is to click on the runestone table of contents, hit project 11 over here, and voila. Or go to the module 8 overview on Canvas if you're on Canvas and hit Tuesday as opposed to Thursday. You know, it's hard in this crazy year of 2020 to remember what day is what. But today is Tuesday. All right, so go ahead. Let's work on the first exercise and split it up into 5 lists. Okay. The next exercise will be figuring out the total top percent, total usage percentage of the top 10 words in the list. Okay. So go ahead and get started. I think this should take about 5 to 7 minutes. Okay. So how have people been able to do this one? All right. It's fairly straightforward. Let's go ahead and say data is equal to data dot read lines, which should work. Should read everything into there. And now what I'm going to do is I'm going to cut off the first line. So for line in data, and then I'm just going to read everything but the first line. Right? So that's a slice of this list that removes index 0. I'm sharing the screen. I haven't stopped sharing. Okay. So I'm just cutting off this bit over here. And so let's see. So we have 5 things. So I'm going to go ahead and copy this for names. So rank is equal to an empty list. Word is equal to an empty list. Part is equal to an empty list. And might as well keep it 4 letters. Freak is equal to an empty list. And dispersion is equal to an empty list, disp. And then for each of these, I'm going to copy this over here into here, but I won't keep these here. I'm just simply copying it for the sake of doing an append operation. So line is equal to line dot split on the comma. So what that will do is that will split it up so that we have comma by comma. So what this will do is that basically this will, split this up into 5 fields. Index 0, 1, 2, 3, 4 fields. And so let's go ahead and do rank dot append. Copy this. So rank dot append, actually line 0. And dot append. A lot of copy pasting here. Dot append. Dot append. 4, 3, 2, 1. And we could throw things into int if we had to. And let's go ahead and print out the top 25 words. So print word through 25. Whoops. Here we go. And there's our top 25 words. Make sense to everybody? Did you need to remove the, let's see. So let's go ahead and see. Did it track in our 5th list? So we do have a /n. So one thing we can do to get rid of that is, well, this is a number. So one easy way to get rid of them without actually having to like strip anything and to turn it into more useful data is to do this. Int. So int for that one, and then the frequency should be an int as well. And then we can turn this into a float, and that will cut out that last part. And now if I'll go ahead and share it. There we go. So now let's explore Zipf's law. Right? It's an empirical law formulated using mathematical statistics, zeta distribution. Math, it looks complicated. Let's go back. So what we want to see is the fraction of overall usage our top 10 most common words represent. The first thing we need to do is turn the frequency count for each word into a percentage. Once we have a new column for a table, we can sum up the percentages of the first 10. Well, we don't actually have to. So what's nice is we don't actually have to do. So first off, let's see if it holds from the previous box. No, it does not. So Control A, Control C. or Command A, Command C. If you're using a Mac, Command V. If you're using a Mac there, copy it in. Great. So Zipf's law, right, as they were saying, is that we've got this logarithmic scale here. You can see here that basically that 10 to the 0th. So each of these steps is like 10 times. Sorry, each of these means 10 times less common, I believe. So basically things are not evenly distributed here. In fact, there's a logarithmic distribution. So calculate the total percentage usage of the top 10 words of the list. Store the variables in a variable called top 10. At the same time, calculate the percentage for bottom 10 words in the list and store it in that result in bottom 10. So we want to figure out the percentage, what percentage do the top 10 words make, which let's see what those were. So the, be, and, of, in, to, have, to, it. Interesting that to is in there twice. Why is to in there twice? Because infinitive, one is as an infinitive. So to do something versus a preposition. So they're looking at use cases there. All right. So go ahead and try this one. So what you're going to have to do is make some modification to this file, which I'll go ahead and share anyway in this one. Should work right. So you'll need, so this one will actually work with active code. So let's go ahead and try this. Okay. So again, I'll give you another 5-7 minutes to do this. And so have at it. And mute myself. So How are people doing on this one? All right. So let's go ahead and go through it because it's actually not too bad. So first off, we have our data already. So to figure out what the percentage of something is, we know how often each thing occurs, right? The occurs this many times, B occurs this many times, C and occurs this many times. So we know how much each thing occurs. So what we need is the total number of times everything occurs. So let's go ahead and I'm going to be lazy and work through it this way, even though it's not necessarily the most efficient. So, well, actually, no, I don't need to be lazy at all. I'm just going to just simply work through it this way. So as we're creating this, I'm going to go ahead and say total. Actually, I don't even need to do this. I already know what the total is going to be. The total is going to be the sum. So what I can do is I can say word 0, for instance, divide by sum of word. That's the percentage of times word 0, the, will occur. So if we save that and run that, it says we passed none of the tests because unsupported type and add for int and string on line 18. Oh, right, because that's the word. What I want is frequency. So the occurs 0.06% of the time. Okay, so we just need that for the top 10 words. So top underscore 10 is equal to, let's go ahead and do, so it would be the sum of word, the sum of the whole thing. I'm just going to do this in one line because I don't know if, rather than doing it in a for loop. And then the first 10 words and sum that up. Does that make sense to everybody? Now you could have done it in a for loop. There's nothing. That's initially how I thought I would do it, but then I remembered that I had the sum function. Top 10 is not defined. Ah, quiet you. That was an intentional mistake, of course. So there we go. We got our value, our sum of our top 10 frequencies. So the top 10 words occur 27% of the time. Make sense in how we did that? So rather than using, so here I just simply took advantage of the sum function and the slicing function. In fact, that we had already split everything up into lists. That made everything super useful. Now, of course, I could have done a for loop, added up total, then added up the first, then done a for loop over the first 10 and added those up and done a for loop on the bottom 10 and add those up. But Python has this useful feature of slicing. It has these useful features of, so it has these useful features of slicing, so I might as well use it. So let's see, -10 to the end. For bottom, right, -10 goes in reverse. And that's how often our other things occur, which is pretty interesting. Now I'm going to do the next part yourself because it's like, okay, just to get a sense of the distribution of words, let's use Altair to graph the frequency of words where the y-axis is the rank of the words, and y-axis is the frequency, and the rank is the x. You should see a pretty dramatic exponential curve. It's also not very useful because a few very large values dwarf all the small values. Okay, so let's go ahead and I'm going to just show you very quickly how to graph, right, which is on this page. Graphing, this is from the Kiva data that they were using, graphing it with Altair. What, this code? It's just 2 lines. I've shared it, and I want to keep moving on this. So it turns out that, and I'm going to do this part. It turns out Altair is actually not that hard to run. Let's go ahead and see an XY graph. Okay, grab it. And let's just take a look at it, what it does. So first thing we need to use Altair is to import it. Makes sense. X values are these values from -10 to 11. Y values are, we go through and we square each of the values in there. Then we simply say our X data is equal to our X vals, our Y values are equal to our Y vals. And then we say encode. Over here, we say chart is we say Altair.chart, mark, and encode. And so let's just play around and see what happens if I call this Ublek. Does that matter? Okay, that just changes the thing, but apparently it has to match. It has to match this, I guess. So if I were to do that. Interesting. Okay. So now I know, believe it or not, I know everything I need to know to use this library, even though I've used it once in my life before. Laser. Annie. Okay, so let's go ahead and do this. Whoops. So we've got our for loop over here. We've got all this stuff over here for reading. Save it and run it. Still runs, great. So we don't need this anymore. Okay. So now our X, we don't need the X values and Y values. What we're going to say is that the data. So let's see. So we want our Y-axis to be our frequency, right? Sorry, X-axis is to be what? X-axis is the rank. So we're going to say rank. Y-axis is let's call it I'm going to call it ranking so I don't get it too confused with our list. And then this is supposed to be a list. So let's say that our rank, that we're going to create a argument called ranking is equal to rank, because we have that list. And then let's spell frequency right. No, this seems like magic, but really this is part of Python being awesome. And we have a graph there. Scalable vector graphics, so we can zoom in as much as we want, and we can see that basically that those highly ranked words make up the vast majority of the frequency, right? So we get into this situation over here where log scales are for quitters who can't find enough paper to make their point properly, right? Where here's the fuel energy density in megajoules per kilogram, and uranium dwarfs everything else. So this goes totally bonkers if you, so basically what we'll do is that we could use logarithms to our advantage. So let's see, frequency. So let's go ahead and compute the logarithm, use the logarithm of the frequency and the logarithm of the rank. And let's see what happens. So rather than doing this, we're going to do math.log. So basically we're taking the logarithm. Now, how many of you actually understand what a logarithm is? Or are just like, that's a thing and I put it into the calculator and hope it works? Because let me tell you, I don't feel like math really teaches like the easiest way to think of logarithms. Okay. So save and run. Oh, right. Have to import math now because save and run. And there we see basically that we get a much more kind of linear, that basically that we've got this logarithmic ranking, where here 8 is basically means 10 to the 8th power, right? 7 over here would mean 10 to the 7th power, where that's basic. And this makes sense because that's around, this would be around 2 million usage, 22 million usages, which corresponds to what we have here. And so we see that basically that the frequent words occur the infrequent words occur a couple thousand times, but that's nothing compared to this. Now, if I didn't take the log over here, then you see that basically that the first couple ones simply dominate everything. Now, this was actually fairly easy to use, and that's part of the awesome thing of Python is that you can look at something, experiment with it, and change it a bit and see what happens and see what's going to work. Now, so with regards to logarithms and how to think that they work, the easiest way to think about how a logarithm works is how many times you can split something by the base. So for instance, if we're going to look at, okay, let me grab this. Okay, that's not nearly long enough. Okay, sorry, I've got to plug in my Wacom tablet here, because I think this is an important lesson for everybody, but, you know, I have certain opinions about mathematics education in general, just not, which is not necessarily Temple, but more about high school education. Okay. So let's go to the whiteboard. So, got it, new whiteboard. So if we wanted to take log base 2 of 16, right? Basically, this asks how many times I can split 16. I can split 16 in piles of 2. So 16 can be split into 2 8s. Each of the 8s can be split into 2 4s. Each of the 4s can be split into 2 2s, and each of the 2s can be split into 1s. For a grand total of 1, 2, 3, 4 splits, right? That makes sense to everybody? And so and if we look at, and if we actually plug that into the relationship that we're supposed to, which is 2 to the 4th is equal to 16, right? We get the answer, right? So it would work for 64, right? Because with 64, you can split that into 32, split 32 into 16. And we already know that this is already can be split into 4 times. So it's a very useful way to think about how many times you can split something into equal piles. Works for a same base. So if we were to take log base 10 of 1,000, 4, 5, 6, 7, 8, 9, 10, right? We can split it into 10 piles of 100, and then we can split each of those piles into 10 piles of 10, and then we can split each of those piles 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 into 10 piles of 1 for a grand total of 3 splits of 10, right? Because we're doing log base 10. Now, you might be asking, well, that's great, but what about 1,002? Well, it would just be a teensy bit more than 3. Or logarithm or log 10 of 1,003 would just be a teensy more than 3. So it kind of breaks down when you're not doing even logarithms, but the logarithmic relationship you're looking for is how many times you can split something. All right, so now let's take a look at the last exercises. Well, let me share this with you so you can play with it. Okay, let's take a look at the last exercises. More fun with words. So we can have some very interesting questions now about lists. Oh, sorry, about words. So which of the words when spelled forward are also on the list when you spell them backwards? So for instance, pot, and that's one of the most common. And you would also could get top. Another common word that's the same that's not the same, that's not palindrome, right? Like race car is, right? Race car is a palindrome spelled forward and backwards the same way. But another one of those where it's still a word if you spell it backwards, flow and wolf, right? Those are 2 words. So, all right. So again, what you would want to do is use this bit that you already have here where you're opening the file, copy it, paste it into here so that you can get your word thing and just find out, hey, how many of these words are in there? So go ahead and give that one a try, right? You want to see, hey, ask how many words or which words, when you spell them backwards, are also in the list. So another 7 minutes on that one. Just to elaborate, you won't need any of the graphing code. That was just something I was doing as a cherry on top for stuff. So don't worry about that if you didn't get it. I was just trying to demonstrate, oh, I haven't seen this before. Let me just tweak this a bit. Okay, and that worked. And that's a very common thing you do when you get comfortable with programming, to just be able to kind of go, huh, if I tweak this, can I use it? You don't need any of the graphing stuff in this one. All right. So how'd this go for everybody? So this one is fairly straightforward. If you think about, once you think about it, it can be hard to think about it if you're panicking and trying to figure out how to do it, but that's okay. So this one is, let's see. So let's go ahead and I'm going to create a new list called reverses. Yeah. Reverse is equal to append. And what we're going to do is that we are going to say for W in word, so for every word in the word list, what we're going to do is we're going to ask, hey, W, we're going to ask if W in reverse, so how do we do reverse? That gives me a reverse right there. In word, let's just restart. I'm trying to charge something and it's not cooperating. So for W in word, if this is in word, right? So for each word, if the reverse of it is also in there, then let's go ahead and say reverse dot append W, or the reverse of it. So let's put in, we'll just put in W, because if it's in the list, then its reverse will be in there and that will trigger and that will get added as well. So print reverse. Go ahead and see. Going, it's doing something. There we go. Oh yeah, A, I, on, no, part, tarp, pool, loop, tip, flow, wolf, live, evil, raw, war, civic, right? It's in the reverse of it isn't there. So I don't know. I mean, you can make an argument either way for them to count or not to count. It didn't specify in the it didn't really specify in this, did it? So all right. So now let's see how many new words can be reversed if you add an S onto the end. So this one's fairly straightforward. How many words can be reversed if you add an S to the end? For example, adding an S to the end of pot gives you stop when reversed, which is definitely on the list. So let's go ahead and share that. And so let's go ahead and work on this last exercise here. Now, I do have things I do have obligations that I have to do, that I have to meet after this class, so I won't be able to stay behind. But if you send me an email, I should be able to meet this evening. So let's work on the last one. How many new words can be reversed if you add an S to the end?
That was an empty box that was upstairs. There's nothing in it.
Okay, so let's go ahead and finish this up and then I'll dismiss the class. So let's go ahead and take a look at the last one. So more fun with words. Let's go ahead and take this. So we were going to see which words were going to happen if you added S to the end of the word, which is fairly simple. Which is just, so if we add S to the end of pot to make it pots, the question is, how many other words do we have? And this takes a long time to run. And the reason for that is because inside this for loop, we have the, okay, here, we're adding the S. So it doesn't really make sense. So what should we do? We should instead add the reverse in this case, because that makes more sense. And it takes a long time because that in operation that we do it for every word. So it takes a while. So we're running a for loop over the entire operation. In a for loop, we're running over the entire operation, which means, for those of you who know big O notation, that means it's an n squared, a quadratic operation. Let's see. So deep turned into speed, top turned into spot, no turned into sun. Why is sun on there multiple times? Probably because no is in our list multiple times, I would guess. Control F, no. I would guess that no is in the list multiple times by itself. That's me, Mike. So sun, right? Suns would be nos, which would be n. So I'm not sure, but I think that basically that maybe no is used multiple times as different parts of speeches. So oh, right. I can search for it by going comma, no, comma. There we go. So it's there once as a D, which is a pronoun. Interesting. As an article. And as a R, which is a adverb. And as a U, which is a interjection. Makes sense there. So what they're seeing there is that there are multiple there are words that have multiple uses in there, but they are also, they're in there because they are multiple parts of speech. All right. So next, so that's today's exercise. And what we're going to do for tomorrow, for Thursday, is we're going to work on the, don't worry about the last part. We're going to work on converting Roman numerals over here. And we're going to see, and we're going to work on that one because that one's going to be make good use of dictionary functions. All right. So everybody take it easy. Have a good week.